Okay, so in this video, now we are at linear correlation and that wonder, that jewel of statistics. So in this video, I'm going to start by assuming that you understand the mean, errors about the mean, standard deviation, and z-scores. If you don't understand those things yet, go back and watch my videos on those topics first, because this one will be confusing and hard to understand if you don't know those statistics fairly well by now. A big part of the frustration of statistics novices, people who are just starting out learning statistics, I think, is that in a class they're forced to move forward before they really understand the foundational material. If you're in that spot and need correlation right now, those other videos won't take you more than an hour to get through, and then this one will make a lot more sense. Alright, so let's suppose that we've measured two variables, like annual income and length of time that a car has been owned. The units of income are thousands of dollars per year. So for example, that first person in our sample makes $20,000 a year. Time that they've owned their car is in months. So this person has owned their current car for 48 months. Okay? Now, by convention, we'll call income our x variable and months with the same old car as our y variable. We can start with a very basic descriptive analysis of the variables, and it would be a good exercise for you, if you are a beginner, to stop the video right here for a few minutes and do the basics by hand. Mean, sums of squares, variance, and standard deviation. Do that and then come back to the video. Alright, did you do that? I don't think you did that. Well, anyway, here you go. Here is your basic descriptive analysis. Okay, and just a really quick review, right? Here are the original distributions that we measured. Here are the deviations about the mean and squared deviations about the mean for both distributions. And of course, here are our sums of squares for both distributions. And the reason we have to square the deviations about the mean, right, is because if we just add up the deviations themselves, they always add up to the same old number, 0. And that's why we like the mean, because it gives 0 net error. So here are our means. And of course, if we take the average squared deviation about the mean, or the average squared error, we get the variance in both cases, right? So this is just 1600 divided by, remember this is a sample, so we don't divide by the total sample size n, we divide by n minus 1 to get the variance, and then take the square root of the variance to get the standard deviation. Okay, now we can ask a really interesting question. Is the length of time that you've had your car related to your income? Just looking at the raw data, it seems like maybe it is. It looks like people who have lower income maybe have higher numbers on average for length of time that they've owned their current car. And as we go up in income, it looks like the number of months that we've owned our car maybe goes down a little bit. A really valuable first step is usually to look at a scatter plot of the two variables and see if there looks like there might be a relationship. So let's have a look at that scatter plot. Alright, so here's the scatter plot. In a scatter plot, you just put your x variable on the x-axis, your y variable on the y-axis, and it actually doesn't matter which is which. Correlation is non-directional, meaning the correlation of x with y is the same as the correlation of y with x. So you could pick actually either one, but usually you do have a variable that you're interested in being your outcome variable, and a variable that you're interested in being the predictor, or the variable that you use to predict the outcome variable. And that will usually influence, if not dictate, your decision about which thing to put on the x-axis. Anyway, that's kind of off topic. Let's go back to looking at our data and our scatter plot, and it does look like, yeah, there's a trend downward as income goes up. The months that you've owned your current car goes down. Obviously, these data are made up. Real scatter plots never look, this clean and nice and stuff. But it does look like there's a general trend downward. So maybe it's realistic to ask if there is a relationship between income and months of car ownership. So what we're working toward, what our goal is here, is to have a single number to tell us to what extent there is a relationship. To what extent does months of car ownership go down with increasing income? But we have a problem, a big problem right out of the gate. And that is we're trying to compare this distribution to this distribution, and they're in different units, right? Remember, income is in units of thousands of dollars per year, and car ownership, duration of car ownership, is in units of months. So this 20 here can't directly be compared to this 48 because this is $20,000 a year and this is 48 months. These are different scales. So it's apples to oranges, dollars to donuts. Same thing. So how can we get around that first hurdle? If only there was a way to transform any scale into a single common scale so that the units would be the same. Anything ring a bell there? Do you have any recollection of anything like that we've talked about before? Maybe in a different video. Maybe a video about z-scores. What units are the z-scores in? Remember that they are in units of standard deviation. So if I standardize the income distribution, it will be in standardized units. And if I standardize the months distribution, it will also be in units of standard deviations. All right. So here's the formula for z-score, in case you forgot. If you're new to stats and trying to understand this stuff, this would be another good opportunity to practice by pausing the video and calculating at least a couple of the z-scores for each variable. So pause here, and if you just want to plow on, here we go. All right, so there are our z-scores for every individual observation. So this z-score right here is the z-score for this observation of income. This z-score right here, this 0, is the z-score for this number of months of car ownership, and so on. All right, so let's look at that first pair. Let's look at the first pair of z-scores. The -1 here means one standard deviation below the mean, right? Remember, z-scores are in units of standard deviation, and the negative, because all z-score distributions, all standardized distributions, have a mean of 0. So a negative z-score means that that observation was below the mean of its distribution. So one standard deviation below the mean. The 1.4715 here, right next to it, means 1.4715 standard deviations above the mean. So the person who is one standard deviation below the mean income has owned their car 1.47 standard deviations longer than the average time of car ownership. Okay, so now we need to come up with a single number that will describe the relationship, including information about whether the two members of the pair are big or small, and alike in both being above or below the mean, or unlike each other, meaning that one is above the mean and the other is below the mean. So I need a single number for each pair that reflects their similarity, including their size, in other words, how far they are from 0, and their togetherness, whether they're both on the same side of the mean or not. And one number that will do this is the product. In other words, multiply the numbers together. Think about it. If both numbers are big and positive, the product will be big and positive. If both numbers are really, really small and positive, the product is small and positive. And if both numbers are negative and really small, meaning really far from the mean, or bigly negative, you can think of it as, in other words, they're very far from the mean, but they're negative, so we can't really say they're big, they're small, but they're really far from 0, the product is going to be big and positive, right? Because when you multiply two negative numbers together, the product is positive. So, and if these numbers are on different sides of their respective distributions, meaning one is above the mean and one is below the mean, then the product is going to be negative, right? Because one of these z-scores is going to be positive and one's going to be negative. And that would indicate that they don't go together at all. They're very different from each other. They're not similar at all. For example, that's what's going to happen right here, right? Because this one is below the mean, this one's above the mean. Multiply these two numbers together, and we're going to get a negative number, indicating that these two numbers are on opposite sides of the mean of their respective distributions. All right, so let's do that for a few of these. try that first one, and what happens? Well, if you pause the video, you can do it with a hand calculator. Otherwise, here it is, right? There is the... you could probably have done that one in your head, now that I think about it. Look at that. It's just negative 1 times that. 1 times anything is the same thing. Negative 1 times anything is the same thing, just negative. So there you go. Negative. Okay, so we get a number that's negative, and that tells us that one of these numbers is above its mean and one is below its mean, and its size tells us how far above and below their means these two numbers were. And if we do the rest, we get a bunch of numbers. And it sure looks like most of them are negative, meaning that one member of each pair is above its mean and the other is below its mean, because one z-score is positive and one is negative. So the product is negative. But now I've got a bunch of numbers, and it's hard to think about a bunch of numbers. Imagine if these were real data and I had hundreds or even millions of numbers. I don't want to think about hundreds or millions of numbers. I want to think about a single number. I want a single number that summarizes all of these products. Can you think of anything? Any ideas? Well, forget for a moment where these numbers came from. Forget all of this hassle that we had to go through to get to these numbers. Just pretend that you had measured something like, I don't know, the size of fish caught in a day, or the number of pennies found in a day, or, you know, the, I don't know, number of pictures bought, whatever. It doesn't matter. You've measured some stuff. You've measured something. How tall a group of people are. What? It doesn't matter. You've got a set of numbers. You want to summarize how much of that stuff there is, how much of that stuff that you've measured is. What statistic do you use in that case? Hopefully you've thought by now, hopefully you've come up with a solution, right? You're probably screaming it at your computer screen even as we speak. The mean, right? The mean. Notice how this formula that I've put here is just the mean, except instead of an x right here, right, sum of x divided by n, I've got a sum of these numbers right here. We're just going to add these numbers up and divide by n. That's the mean, right? So it's still just saying the same thing. Now, we're not quite done yet, but conceptually we're done. Conceptually, that's the number that we're going for. We're going for the mean of these products. We have to adjust. We have to make one slight adjustment. It's really very similar to when we had to make an adjustment for the variance formula for a sample. And in fact, it's the same adjustment. We have to subtract 1 from the sample size. We're still taking an average. We're just adjusting the denominator so that we're not taking the average based on the entire sample size, but by 1 less than the entire sample size. But it's still doing the same thing. It's the average standardized product. And we usually symbolize it with the lowercase letter r when it is the sample standardized product. And this statistic has a name. Its full given name, it's kind of a mouthful. It's the Pearson product moment correlation coefficient. The Pearson product moment correlation coefficient. Now that's a lot to say, so most people just call it the correlation. And this is it. This is the correlation. The correlation is just a mean. See, this whole time you thought it was going to be hard to understand, you thought it was going to be confusing. Nah, it's just a mean. You know, I guess this part maybe is still a little confusing to you. Why these numbers somehow describe the similarity of their respective pairs, right? How similar are these pairs? Well, this number kind of describes it. If it's negative, they were on different sides of their mean. If it's small, they were really close to their respective means. If it's big, that they were relatively far from their respective means, and so on. But it's probably not terribly difficult for you at this point to understand. Once you have those numbers, you can describe the average degree of similarity in across all the pairs by taking the average, and that's what the correlation is. All right. So in our particular case, here it is worked out for our specific example. So you just add up all of these products, come up with this number right here, fill it in the equation on top, divide by n minus 1, and you come up with the Pearson product moment correlation coefficient, or the correlation. All right. A few things. a few things about R that make it really handy to interpret. First, it can only range between -1 and +1. The formula just can't make numbers outside that range if your calculations are correct. A positive correlation means that as x increases, y also increases. A negative correlation means that if x increases, y decreases. And the closer to 1 or +1 or -1, the stronger the correlation. The closer to 0, the weaker the correlation. But correlations, even if they're negative, can still be strong. So a correlation of -0.8, -0.9, that's a really strong correlation. It's just negative. And all negative means, negative doesn't mean bad. It just means as one goes up, the other goes down. So very often, negative correlations are actually really good. We want negative correlations in some cases. And please, for the safety of all humanity, keep in mind that correlation does not imply causation. In fact, no statistic implies causation. Causation has to be inferred from experimental design, not from any statistic, although statistics can play a role in establishing correlation. I'll have another video on that, blah, blah, blah. But just because x and y are correlated, that does not mean that x causes y. I'll do a whole video on specifically why that's not the case. Why is it that we cannot imply correlation from why can we not imply causation from correlation? But that's enough for now. That's your crash course in the correlation. Hopefully you understand that a little bit better now.